Right, so actually before I just continue on, after talking to a few grad students yesterday, I thought I should maybe give a quick review about how Higgs bundles work on a fixed Riemann surface, and just to kind of see quickly the picture that we're trying to to build up on. And I'll just remind you what those objects are after I do this. Okay, so this is just a quick review of I'll say SLNC Higgs bundles in terms of vector bundles on a fixed Riemann surface X. Okay, so let me just remind you what, or tell you what they are. So well, it's a pair, E phi, where E over X is a rank n holomorphic vector bundle. And I'm going to assume its determinant bundle is trivial. That's the S bit. And phi is let me reuse this. It's a 1-0 form valued in the endomorphism bundle of E. Its trace is 0. That's the algebra condition of this group. And there's a compatibility condition between these things, namely, it's holomorphic. Okay, so that's what a Higgs bundle is, and let me just say, so E phi is stable. So if, well, for all sub-Higgs bundles, you have a slope stability condition. So for all F that are proper in E, and phi of F is contained in F, okay? So I think I was using, maybe I wasn't using a notation yet, so I'll use K for the cotangent bundle. So if the Higgs field has an endomorphism, one form valued in endomorphisms maps F to itself, twisted by the cotangent bundle, then, so for all these, the slope of F is less than the slope of E, and since I assumed the determinant was trivial, that's always 0. Okay, so there's a group that acts on the set of Higgs bundles. This is the set of, it's called the gauge group. So they're bundle automorphisms of the smooth complex vector bundle, which cover the identity. Okay? Oh, right. Well, G, and the determinant of G is the identity. So it induces the identity on the determinant. And this group acts on Higgs bundles. It acts. Okay, and so let's fix a Hermitian metric H on E. So this should be looking a lot like Rui's talk. Where am I? And from my Higgs bundle, well, I have a holomorphic structure and a one form valued in endomorphisms. And so my metric associates a Chern connection to the holomorphic structure, and I can also take adjoints of endomorphisms. The adjoint of the Higgs field is a 0-1 form valued in endomorphisms. And from this data, I can build a connection, B, which is the sum of these things. And I'll define a function, which is called R of a Higgs field, which is defined to be the curvature of that connection. Okay, and it turns out that that's equal to, by the holomorphicity of phi, the curvature of the Chern connection plus phi bracket phi star. Okay, so these are known as the Higgs bundle equations or the Hitchin equations or the self-duality equation. And the theorem, let's say Hitchin Simpson, is, so if I take a stable Higgs bundle, well, a Higgs bundle is stable if and only if there exists a gauge transformation so that R of G dot E phi is equal to 0. Namely, the curvature of this connection, which is not the unitary connection, but this connection with holonomy in the SLNC is flat. And I said if and only if, so let me make sure I say, and G is unique up to the gauge group, which is the unitary gauge group. Okay, and so this moduli space MX SLNC of stable Higgs bundles for the group SLNC, so these is stable E phi up to gauge, it can also be constructed, let's say, a stable E phi in R inverse of 0. So int R is something related to a moment map, like in Rui's talk, mod the unitary gauge group. Okay, and the map now, which is what I was calling HX last time, to the character variety, SLNC, is defined by taking the holonomy of the flat connection okay, great. So as a quick example, what is an example of a more concrete Higgs bundle? E I'll take to be a rank 3 bundle. It's going to be the direct sum of 3 line bundles, the cotangent bundle, the trivial bundle, and the tangent bundle. And the Higgs field is going to be in this holomorphic decomposition. I'll write it's going to be this matrix, which is, if you properly interpret it, is a one-form valued in endomorphisms of E. Okay, and in this case, Hx of E is, so this is like the one case where you can really say exactly what the associated representation is. So this is going to be my representation rho in the fundamental group. It turns out it lands in SO21, and it's the uniformizing representation of the Riemann surface. Okay, so this is my quick overview of Higgs bundles. Hopefully, now let's, so are there any questions first? Yeah. So it says stable, and then somehow you need to parse this if and only if with this uniqueness part. So yeah, okay, so you really would say polystable with existence. Okay, I think you know what the correct statement is. Yeah, I wanted to say an if and only if, but I knew it wasn't true unless I added. You can solve, well, you can, Nigel, solve the equations. You see that solving them is equivalent to finding a metric here of constant curvature. So it's really, a direct thing. Okay, great. So now let me remind you what we were saying last time. So this was our setup. I had this big space JP, which was the thing which is keeping track of the holomorphic structures on a principal bundle. And from this perspective, I don't need to pick a choice of Riemann surface. That kind of is already built in. Namely, there's a projection map to complex structures on the surface. And I'm going to think of one forms valued in the adjoint bundle on the total space of the principal bundle. And those are exactly sections of Hom from the tangent bundle to the vertical bundle that are equivariant and vanish on the vertical piece. Okay, and then finally, our main object of interest is this space C, which sits inside the product of J and this space. It's a space of pairs where you have a complex structure and a phi, and they satisfy this equation, which says that phi has type 1, 0. Okay, and now we can map down to almost complex structures. Okay, so it's just like this part of the definition without the holomorphism. Okay, and then an important thing now when the Riemann surface isn't fixed is that the tangent space of this object is a set of pairs m theta. So m is a tangent vector to the holomorphic structures, and theta is just an element of this vector space. But the important relation that you get by differentiating this condition is that the tangent vector theta is not a 1-0 form. It has a 0-1 part, and the 0-1 part is uniquely determined by the point you're at. Okay, this equation says that phi composed m is equal to up to a factor of 1/2i, the 0-1 part of theta. The 1-0 part is completely free, and the 0-1 part is determined by the point you're at. But it's usually not 0. Okay. Great. And so let me just remind you, the goal, my goal at least, for today is to define this almost complex structure, omega naught and h naught and theta on this big configuration space. And really the important goal is to explain why there's a minus sign, or why you get something that on the actual moduli space that's pseudo-Hermitian and not actually Hermitian. Okay, and it comes exactly from this condition. Okay, great. So last time I already accomplished this goal for I, and the natural complex structure on the configuration space is just you post-compose with J. Okay, so it depends on the point you're at. And since theta, if I think of it and in this terms, it's a Hom from the tangent bundle to the vertical bundle, and then I act by J. Remember that J acts as I on the vertical bundle. Okay, so this is just multiplication by I on this vector space. If you pre-composed by J, then it would act by multiplication by I on the 1-0 part and minus I on the 0-1 part. Okay, and that's not what you're doing, and so it's important that this condition, I mean, if you define it like this, C is a holomorphic submanifold of this product. Okay. Okay, I guess I'll just erase. Okay, so let me talk about connections and like the analog of the Chern connection for principal bundles. So connections on a principal bundle P. So AP is the set. So there's lots of ways to think about connections, as we probably all know, but I'm going to think about it like this. So they're going to be homomorphisms from the tangent bundle of P to the vertical bundle of P that are equivariant, such that when I restrict them to the vertical bundle, I get the identity. Okay, so such a B is equivalent to giving me a G equivariant splitting of my tangent bundle as the vertical bundle plus a horizontal piece, which I'll denote by HB. This is the, kernel of B, if I think about it like this. All right. And the space of connections is affine over this space, where I think about it, the right-hand side, you see it very clearly. Okay, good. So now let me fix K and G a maximal compact subgroup. Okay, so we know what those are. Rui just told us. If you like SU, SLNC, you're exactly looking at the special unitary group. And I also want to fix a structure group reduction of my principal G bundle to K. Okay, this is the principal bundle version of picking a Hermitian metric and fixing it. Okay, so you can always do this because G and K are homotopy equivalent. Okay, good. And so if you, now I can look at the space of connections on the K bundle. So these are the analog of unitary connections. And I can think of those in sitting inside or special types of G connections. Okay, great. So here's a fact, which is the Chern connection, or we're calling it the Chern-Singer connection. Well, there's a map these holomorphic structures on the principal bundle to the space of unitary connections across complex structures on the base, which is an isomorphism. Okay, and so what does it do? It takes a J and sends it to something I'll call AJ, and then IJ, the one induced downstairs. And this guy is the Chern-Singer connection associated to J. Okay, and it's characterized just like before, like in the vector bundle thing, that this connection, one, it's unitary by definition, and two, it has type 1,0 with respect to the complex structure. Okay, so that's the condition AJ composed J is equal to I AJ. Okay, great. And here's maybe a more useful way to think about it, or a useful way to think about it. So given a unitary connection and a complex structure on the surface, how do you write down the associated complex structure on the principal bundle? Well, you work in the splitting given by your unitary connection. Like a less squeaky. Oh, yeah, that's better. Okay, so in this splitting, S inverse of AJ, namely the holomorphic structure associated to this this data, is just I, or that's multiplication by I on the vertical piece. That's one of the necessary conditions. 0, 0, and then J. J on the horizontal piece, which is isomorphic to the pullback of the tangent bundle. Okay, and in this splitting also, the connection, of course, looks like this. And a Higgs field, I mean, I'm not saying anything deep here, but this is the type of object it is. It maps you, okay, it's one of the objects that, say that. It takes values in the vertical bundle and vanishes on vertical vector. Okay, good. So here's, the main point I want to do is I want to, tell you about these metrics, about these forms, H naught, omega naught, and so on, and theta. And there are things that are going to be on the tangent space to see. So I need a kind of I'm going to now write down I'll just write down the following lemma, which describes the tangent vectors in a more, useful way. Okay, so lemma or m theta in the tangent space at j phi to c in the splitting of the Chern connection, we have m is 0, 0, beta m, and theta is 0, 0, 0, psi plus 1 over 2i phi mu. Where, well, what are these objects? Well, what is little m? Little m is the image of big M under the projection map. Okay, and this mu over here, let me write it a little bigger, is related to little m. So little m, if I complexify it, looks like this. So it's an endomorphism of the complexified tangent bundle. And the condition of it being a tangent vector to complex structures means it has this form. So in particular, mu here maps me from the 1, 0 part to the 0, 1 part. Okay, so that means it's a 0, 1 form valued in the 1, 0 part of the tangent. Okay, and this object is called a Beltrami differential. Okay, so that's this mu term here. And now what are beta and psi? Well, beta is a 0, 1 form valued in the adjoint bundle. And psi is a 1, 0 form valued in the adjoint. Okay, so this is the theta, but theta is decomposed into its 1, 0 part and its 0, 1 part. Its 1, 0 part can be whatever you want, and its 0, 1 part, by what we said before, has to be 1 over 2i phi mu. Okay, so the proof, so I'll leave that as an exercise. You should use Jm plus Mj 0. You should use phi, looks like this, and is of type 1, 0 to get just the 1, 0 part there. And you should use the yellow box over there, which I called star in my notes, but I'm not going to go all the way over there to call it star here. Okay. Good. Okay, so the point is that the if I look at the tangent bundle, tangent space here, a vector in here is determined by this data mu, beta, and theta, where theta is a 1, 0 thing plus 1 over 2i phi mu. And in this formulation, the complex structure applied to such a vector is just multiply all the factors by I. Okay. Okay, good. Okay, great. So here's an exercise 2. What is the derivative of this map S? Okay, so I'm going to, okay, so we're going to need this when I try to pull back the Atiyah-Goldman form. The derivative of this map S. Okay, and this is another time where you get a factor of 1 over 2i because you're working with holomorphic structures on a principal bundle and not like d-bar operators. So as an exercise, the derivative of the map S on a vector big M, which I'm going to decompose as a little m and a beta, is equal to 1 over 2i beta minus 1 over 2i beta star. Oh, I haven't talked about adjoints yet, but it's okay, we'll get there in a second. Comma m. And this is our second factor of 1 over 2i. That kind of is annoyingly showing up. Okay, great. So now I can define theta for you. Okay, so theta is super easy to define, it turns out. And it's kind of mysterious to me still how such a simple object can be kind of important for so many different reasons, or from so many different perspectives. Okay, so definition of theta. So maybe I should stop. Are there any questions? Okay, great. So definition of theta. Well, remember, well, what should it do? Theta, you have this tangent bundle of the configuration space. You have d pi to the tangent bundle of almost complex structures on the surface. And then you have the vertical bundle, kernel of d pi. And theta is a map like this. So it's not quite a way of lifting tangent vectors to complex structures on the surface here, because they go all the way to the kernel of the projection map. Okay, so when you project down, you always get 0. Okay, so what is the definition? The theta at a point j phi of mu is going to be equal to 0. So this is, maybe I should say it's mu beta theta equal to, so this I'm just going to write it in this, in terms of the tangent vector decomposition I just gave. It's 0, 1 over 2i phi mu, 0. Okay, so that's the definition. So what are you kind of doing if on Higgs bundles for a fixed Riemann surface? You're using a Beltrami differential and your Higgs field to deform the d-bar operator exactly by adding this element to the d-bar operator. 1 over 2i, your Higgs field composed with mu. Just to be clear, phi mu is a 0-1 form than the adjoint bundle. So it's a type of thing you can deform a d-bar operator with. And you really get a new Higgs bundle exactly, because the Higgs field commutes with itself. Okay, so that's the definition of theta. And maybe I just say, so if you remember, theta is identically 0 if the Higgs field is 0. And if you remember, the kernel of theta was related to the complex directions in this isomonodromic distribution. Okay, so if your Higgs field is identically 0, then theta is always 0, which means that your isomonodromic distribution is always complex. Okay, and this is a way to see that compact representations, the ones that are associated to Higgs field 0, have holomorphic isomonodromic leaves. Okay, and this was proven by Biswas, at least for SLNC, some time ago, but anyways, you get a kind of a new perspective on that fact. Okay, so that's theta. Okay, maybe I should say one more thing just so I don't mislead you. This thing is only 0 on the configuration space when the Higgs field is 0. Okay, but being 0 on the moduli space is that this thing is in gauge orbit, right? Okay, so that's not equivalent to the Higgs field being 0. So anyways, we'll kind of come to that hopefully next time. Same idea, there are C-star fixed points in the Higgs bundle moduli space that aren't 0. Okay, great. So now I'm after defining this omega naught, and well, I defined I. If I define omega naught, then I can tell you what H naught is, right? Okay, so before I do that, let me say the fixed reduction of structure group to K, namely the fixed Hermitian metric, lets me define adjoints and L2 norms of beta in size. So beta, let me write what I wanted to write. So L2 norms or inner products on the space of 1, 0, and 0, 1 forms. Yeah. By this term. Higgs field does not change. Yeah, the Higgs field doesn't change. That's right. Well, in the nilpotent cone, at least, these are definitely downward directions because you haven't changed the Higgs field and you move your d-bar operator in a lower triangular way because your Higgs field's already lower triangular. I haven't thought. Okay, yeah, we can think about it more and talk about it more. Okay, great. Okay, so here's the kind of lemma I'm gonna now try to explain to you, or like why it's true. For J, phi, and C, this configuration space, and a vector V, which I'll write as mu beta psi, I think, or theta, okay, good. A tangent vector. H naught of V1, V2 is equal to, well, I take just the L2 inner product of beta 1, beta 2 plus the L2 inner product of psi 1, psi 2. Okay, so mu hasn't shown up at all. And now here's the important minus sign. There's a minus 1/4 because of the 1 over 2i by mu 1 by mu 2 L2 inner product. Okay, so in particular, this negative sign here is the reason for this kind of negative directions coming from deforming the complex structure, or negative, tangent directions in the metric. Okay, so great. And it basically becomes from the fact that these are 0, 1 forms and not 1, 0 forms in the order in which they appear in the wedge product. Okay. Good, so that's what I'm gonna try to tell you about right now. So remember how it came up though. So this wasn't you could just write down this thing, it's a good one, but it's not what I would have written down at the beginning. It took me a long time to come to terms with this minus sign, because it seemed like something was, I was making a poor choice previously because I wasn't getting something that looked Kähler. Okay, but where does it come from? It comes from pulling back the Atiyah-Bach-Goldman form, taking an invariant part with respect to the complex structure, and then looking at the associated Hermitian form. Okay, and this is what you get, and that's what I want to explain to you now. Okay, great. So what is the Atiyah-Bach-Goldman form? On the space of connections. So remember, this is a complex structure on the space of flat connections, and it comes from this is a holomorphic symplectic form on the space of flat connections, and it comes from just a complex symplectic form on the space of all connections. Okay, and the space of all connections is affine over this space, so it really comes from just a symplectic form on this vector space. Okay, great. So that's, I'll define it. So it takes 2 1 forms valued in the adjoint bundle and gives you a complex number. And what does it do? Takes sigma 1 and sigma 2 and takes the integral over the surface of some two form. What two form? Well, this is a Lie algebra valued thing, two Lie algebra valued things, so I'm going to kind of get a number out of those things and then wedge the forms. Okay, so here's my notation for how you do that. And so this Kg is the killing form on the Lie algebra. And what this means is I think of at least on elementary tensors, let me just say, omega 1 is, so it's if omega is alpha tensor eta, where this is a Lie algebra valued section and this is a one form, then let me just write it. What I mean by this notation is I get a number out of the Lie algebra valued things, and then I use that function and I multiply it by taking the wedge product of the forms. Okay. Okay, great. So that's the complex maybe I'm not wanting to erase this, but I'm halfway done. So what's the real part? Well, here's where I'm going to use my fixed reduction. Okay, so my fixed pk lets me decompose sections of this adjoint bundle into, well, the point is the Lie algebra is k plus ik. So this came up in Rui's talk. Property of being a reductive group is that it's the complexification of a maximal compact. And so that means when I look at the compact subalgebra, when I complexify it, I get my group, my Lie algebra back. So that just means that I get a decomposition as k plus ik. So this is skew adjoint things and self-adjoint things, or Hermitian matrices. And this is, of course, k invariant. So I get to decompose my bundle like this. That means I can decompose this one form valued section as x plus I y, and I'll just take the real part of Witzia-Bach-Goldman form, sigma 1, sigma 2. Well, you just use the x's with themselves and the y's with themselves, but you get a minus sign because I squared is minus 1. Okay, so that's kg x1 wedge x2 minus y1 wedge y2. Okay, good. Okay, and now another thing that your reduction gives you is a notion of adjoints, just like your metrics allows you to take adjoints. And let me not really say so much, but of course, if you have something in K, which you should think of as SUN, these are things whose adjoints are, well, not themselves, minus themselves. And of course, if I multiply it by I and I take the adjoint, I get I times eta. Okay, good. Okay, and then now one more thing. If I have a one form and a Lie algebra valued section, so here alpha is a one form, just like it was before. Its adjoint is, by definition, conjugate the one form and take the adjoint of the section. Okay, good. Okay, and now here's the important thing. Okay, so let me just write it. So if I have sigma a PQ form, where it's 1, 0, or 0, 1, then the L2 inner product you get from this perspective is equal to, well, it's plus I, the integral sigma 1 wedge sigma 2 star, if you're 1, 0, and it's minus I sigma 1 wedge sigma 2 adjoint for 0, 1 points. Okay, 1 because this is like a DZ bar, wedge of DZ, and you need to flip it, and you always get a minus. Okay, good. Okay, so now let me define the map H. Okay, so now let's talk about this map H from the configuration space to the space of G connections. Okay, what do? So, this is this non-abelian Hodge map. Okay, so I take my J and my phi. I've fixed my background reduction, so I'll take it to the Chern connection of J plus 1 over 2I phi plus 1 over 2I phi star. Okay, here's our last factor of 1 over 2I, but it's there to compensate the other two, or well, at least the second one. Okay. Okay, so now here's by the exercise, which I might have erased, about the derivative of the Singer map, or the map that gives you the Chern connection. What is the derivative? We're going to pull back something, so we need to understand the derivative of this map. Okay, so the derivative of this map H in terms of mu, beta, and theta. So these are tangent vectors to J, and then theta is the tangent vector associated to phi. Well, you take the derivative of this, the Chern connection map, which is 1 over 2I beta minus beta star. Wait, did I get it? Oh, sorry. There's a very confusing thing when you have factors of 1 over 2I and you take adjoints because you have to keep track of all these signs. Okay, so let me just tell you what it is. It's 1 over 2I. I'm going to pull it all the way out front. Now beta plus beta star, and then plus beta minus beta star. Okay, so if you put the 1 over 2I back in, it's 1 over 2I beta minus 1 over 2I beta quantity star, and then plus 1 over 2I theta from here, plus 1 over 2I theta star. Okay, so the reason for this 1 over 2I in the map is so that I can bring this constant all the way out and just think of it in this way. Okay, it's not an important part of the story, but I just wanted to justify why we did it. Okay. Good, so now, what is the pullback of this real part of the Garcia-Prada-Goldman on V1 and V2? The real part. Well, let's see, where did I write it? I wrote it right here. Okay, and now what are the x's? I even wrote it. So x comes from this term. So the skew, the part in the Lie algebra of K is 1 over 2I beta plus beta star. And the y part is here is 1 over 2I beta plus beta star. Okay, good. So now let me just write it down. What do you get? You get, well, probably many of you have seen this before, but let me just go out. The first pieces you get are just the things you always have. So beta 1 wedge beta 2 star plus beta 1 star wedge beta 2 with a minus a fourth out front, plus a fourth. Same thing with the psi. Psi 1 wedge psi 2 star plus psi 1 star wedge psi 2. Sorry. V is going to be mu beta theta. So these should be thetas. Okay, but now you get more because theta is not a 1,0 form. Okay, so this is what you get on a fixed Riemann surface because the tangent direction on this second part is a 1,0 form. But you get another term now, or two more terms if you group them differently, which is theta 1 wedge theta 2 plus theta 1 star wedge theta 2 star. Okay, good. And now recall that I just multiplies all the guys by I. Okay, so this is the thing I want to decompose into its 1,1 part, its 2,0 part, and its 0,2 part. Okay, and since everything comes up here with something and an adjoint, and you multiply by I, this is the 1,1 part. I can't write above because it can't be seen on the recording. So this guy is the 1,1 part with respect to I of this 2 form. And now here I multiply by I on both factors. This guy, or with the integral, is the 2,0 part. And this guy is the 0,2 part. Okay, so now finally, okay, maybe my timing will be good today. See? Any questions? Maybe I should pause. Okay, great. Good, and now the decomposition of theta, let me just write it out. Theta is psi plus 1/2I phi mu implies that the 1,1 part was omega naught, remember? So omega naught of V1, V2 is equal to, well, let me just write it. Okay, plus a fourth. Psi 1 and then plus a 16th because of the 1/2i's, a fourth times a fourth, of the terms here which involve the phi mu and its adjoint. Okay, so that's phi mu1 wedge phi star mu2 bar plus phi star mu1 bar wedge phi mu2. And remember, this is a 0,1 form, but it shows up first. Okay, and that's the reason of the sign. Okay, so something, let me just note, omega naught is closed. Okay, this is not too hard to see. Like this term and this term don't depend on the base point at all. And the base point is the complex structure J. And this thing is closed. And maybe you already knew this thing was closed if you already had done this stuff. So anyways, this plus this is closed. Okay, great. And let me now just write down the 2,0 part, because hopefully at the end of next time I'll be able to say something about this form will show up, the 2, 0 part of this pullback is 1 over 8i okay, psi 1 wedge phi mu 2 plus phi mu 1 wedge psi 2. Okay, so I wrote it down once, and maybe it'll be in your notes, and then next time when I say, when I pull something back in the special, and I restrict it to the special subvariety, note that this expression is already 0. That's okay, why I'm going to write it down. Okay, and now here's an exercise, which is basically exercise. Use this expression and this fact and the definition of I. Remember, H naught of V1, V2, which is by definition 2 times omega naught of I V1, V2 plus I omega naught V1, V2 is equal to that expression there. Okay, just to reiterate or emphasize, right? If mu is 0, this means I'm fixing the Riemann surface. You get exactly what you know, and maybe knew, but and if you did know, you surely love on the fibers. Okay, good. Now this nice Hermitian form, not being positive definite, or not even being non-degenerate because of this minus sign, is a real problem if you want to construct moduli spaces in the maybe classical way, where you construct slices for the action of the automorphism group by, well, smooth things are kind of a nastier topology, so I'm going to use my L2 inner product to complete them to Hilbert manifolds, and then I'll prove my slice theorem by modeling my slice on the space of harmonics in this tangent space, in this first cohomology group, and then kind of building the slice by exponentiating or having a map from the harmonics into the configuration space. To do all of those steps, you need something positive definite and non-degenerate. Okay, and so anyways, that's a problem. And this is why we need this HS. Okay, that's H0 is when S is equal to 0. And maybe why H0 is so nice is because it's just comes from the Tiabak-Golden. Okay, and HS comes from choosing a little more information on your surface. It comes from some natural thing on Teichmüller space, namely the Weil-Petersen metric. But nevertheless, you have to make some extra choices like a conformal structure, a conformal metric on your surface. Okay, so let me define this, and then I think I will end exactly where I wanted to. So the Weil-Petersen form, okay, one is Hermitian, one is a symplectic form, on complex structures on your surface is what I'm going to tell you about now. Okay, so for an almost complex structure on your surface, I'm going to fix Gj, the uniformizing metric. Okay, I think that's close enough. Metric. Okay, so let's say curvature -1. Okay, and so, okay, I better write it up here where it's big and can be seen. Okay, and if I take M1 and M2, tangent vectors for almost complex structures at the point J, then the Hermitian form of the Weil-Petersen metric takes two Beltrami differentials, mu1 and mu2, associated to these points, and it gives you back the number, which is the integral of mu1, mu2 bar, and well, because of the type of tensors these are, this is a function and not a two form, and so you need to integrate it against the volume form you've chosen. Okay, so this is the role of this choice of conformal metric. Okay, and the associated symplectic form, you can define in terms of M1 and M2 and J in a nice way, but let me just write it in terms of Beltrami differentials. Okay, 1/2 integral over sigma, mu1, mu2 bar minus mu1 bar, mu2. Okay, so it's the same type of form as before. One interesting or nice fact is that this form is actually not closed on the big configuration space. Okay, because I need to choose, I'm choosing this uniformizing metric. And you need to understand how that varies as you move your complex structure. But it is closed on Teichmüller space. Okay, so that's, okay, and so now what is HS? Let me just go back here and write it. Okay, I'm not going to cheat and just decorate H, but maybe I should. Okay, so here I kind of have really a map to connections and complex structures on the surface. So H hat goes from C to connections across complex structures on the surface. I take J phi, just to be clear, to H gamma pi J. And for S, any real number, I can pull back the Atiyah-Bach-Goldman form, the real part, and S times the Weil-Petersen form. Okay, and when you do this, you get omega naught plus S times the Weil-Petersen form. Okay, and now what is HS associated to, so it's still of type 1,1, because this is a Kähler form on type, is of type 1,1. So what is this HS inner product on these tangent vectors? It's, let's see, I think I just erased where I said that, but okay, but hopefully remember this is mu beta psi. It's the same type of thing before. But plus S times the Weil-Petersen form, which is positive. Okay, and this term is S minus a fourth norm squared of the Higgs field times mu1, mu2. Okay, so the lemma now, or just calling everything a lemma, but really I want to call it an observation from what I just described to you. For each fixed point of my configuration space, there exists an S naught bigger than or equal to 0, so that HS is a positive definite non-degenerate form, positive for all S bigger than S naught. Okay, and it's this metric which we'll use, depending on the point you're at, to construct harmonics and prove these slices. And the miracle, or a miracle that shows up, is that the harmonics that you actually find using this metric are independent of S. Okay, and I'll say a little more about that next. Thanks.
Questions?
There's a mic there. It's a good question. Really, the answer is yes, if you add some adjectives, but we haven't done it. So the question for the video was, what about in the punctured case? What can you do? You forgot to turn on your mic. It's okay. It's okay. Yeah, it's an interesting case. I have some applications in this punctured case I'd like to understand, specifically the punctured sphere, but we haven't gone through the details of it, and that's where it is.
Any other questions? Thanks again.